Hello everyone, welcome back to my channel. Let's continue our lecture for chapter 4. This video will cover the second part of image representation. This part, we will look into color models, graphics in multimedia product and how to calculate the size of image in the memory. Oh wait, before we start, don't forget to subscribe my channel first. Thank you. Now, let's learn on how colors are produced on screen. Basically, colors are corresponded by 7 wavelength ranges within the visible spectrum. Color from a computer monitor or a TV screen results from a different process that due to reflection. A monitor or TV screen generates 3 colors of light: red, green, and blue, and the different colors we see are due to different combinations and intensities of these 3 primary colors. Each pixel on a computer screen is composed of 3 small dots of compounds called phosphors surrounded by a shadow mask. Then, phosphors emit light when struck by the electron beams produced by the electron guns at the rear of the tube. The 3 separate phosphors produce red, green, and blue light, respectively. Modern color theory is based on 3 primary colors known as additive color or also called as projected color, which are red, green, and blue, and printed colors or the subtractive color, which are cyan, magenta, and yellow. The additive primaries red, green, and blue generate color by beginning with absence of color, black, to generate all colors. The 3 colors are projected onto a screen in various intensities to produce all colors. This principle generates color for televisions, computer monitors and movie screens, that is, all projected color. Printers and anyone working with color on paper or another reflective surface can't work with additive primaries. This is because color reflected from a surface begins with white, or a light color. Keep in mind white is all light together, meaning that ink or paint subtracts from that white to produce the colors you see. The printed page consists of tiny halftone dots of 3 primary colors: cyan, magenta, and yellow, which also known as CMYK, where K is key, which is K is for black. The RGB color model is the most known, and the most everyday. It defines a color space in terms of 3 components of red, green and blue, which ranges from 0 to 255. The RGB color model is an additive one and also known as 3 primary colors. For example, red can be represented as red is 255, green is 0 and blue is 0. Another example is violet, represented as red is 238. Green is 130 and blue is 238. The HSV, hue, saturation, brightness, color model defines a color space in terms of 3 components. Hue is the color type, such as red, blue, or yellow. Ranges from 0 to 360 degrees in most applications where value corresponds to 1 color. 0 is red. 45 is a shade of orange and 55 is a shade of yellow. Saturation is the intensity of the color, which ranges from 0 to 100%, where 0 means no color, that is a shade of gray between black and white, for 100 means intense color. Also sometimes called the purity by analogy to the colorimetric quantities excitation purity. The lower the saturation of a color, the more grayness is present and the more faded the color will appear. Brightness, or value, is the brightness of the color. It ranges from 0 to 100%, where 0 is always black, depending on the saturation, and 100 may be white or a more or less saturated color. The UV model defines a color space in terms of 1 luma and 2 chrominance components and is similar to PR and PCR. The UV color model is used in the PAL, NTSC, and SECAM composite color video standards. UV models human perception of color more closely than the standard RGB model used in computer graphics hardware. The UV color space stands for Y, the luma component, or the brightness, ranges from 0 to 100% in most applications. U and V are the chrominance components, blue luminance and red luminance differences components. Colors should be used according to the target audience's monitor specifications. Normally, customer will select their preferred monitor resolution when buying new stuff like smartphones or computer with higher resolution that suits with their budget. What is image resolution? A high-resolution image is an image with high density of pixels, that is, with several families of pixels in its composition. The greater the number of pixels, the higher the resolution, providing more details and better definition to the image. Logically, an image with low resolution will have less pixels, less details and definition. For example, this Oppo smartphone have higher resolution to produces larger size of image and the rear camera have 25 megapixels to capture larger image information per pixels. The image resolution is determined by the pixels per inch, PPI, and dot per inch, DPI, calculations. PPI is associated with screens of digital devices. Each pixel is equivalent to a point of light coming from any monitor, then the utility of PPI is to report the quantity of pixels on a screen inch. While DPI is similar to PPI, but the pixels, virtual drive, are replaced by the number of points, physical drive, in a printed inch. The more dots the image has, the higher the quality of the print, more sharpness and detail. Let's look at the relationship between PPI and DPI. Since DPI is a reproduction in real size of the image's pin memory space, so it requires more DPI than require PPI for the same file. Then for example of 300 DPI image is equals to 118.11 PPI. For a good printing output, 300 DPI is a standard, but sometimes 150 is acceptable, but never go lower than that. Otherwise, you will print blur image. This table guides you to choose suitable print area, the paper size, for good printing quality. So now let's do some exercise. If let's say you have 1800 x 1200 pixels image. Find out how big will an image be if displayed on a monitor with 300 pin to monitor with 150 pin. Then identify which monitor display larger image. 1800 by 1200 pixels meaning 1800 pixel of height and 1200 pixels of width. So, find physical dimension for height and width by dividing with the device resolution. We get 1800 divided by 300 pi is equal to 6 inches of height and 1200 divided by 300 pi is equal to 4 inches of wide. So the dimension of 1800 by 1200 pixels on 300 pi monitor is 6 by 4 inches. Repeat for 150 pi resolution. We got 12 by 8 inches. So, we conclude that a device with lesser pixels display bigger images. This is another exercise on how to determine the best printing quality for your photos. If let's say you have a 640 by 480 image and you want to print it at 200 pi, determine the recommended paper size for good printing. Here is the solution. Again, divide the height and width of your image with the device resolution. Then your calculation will be 640 divides with 200 pi for height area and 480 divides by 200 for width area. So, your recommended paper size will be 3.2 x 2.4. So, how much storage in your memory cost for one single image that you store? The larger image will consume large memory space. This is what we called as memory cost. Memory cost is computed based on the image size. For this example, what is the memory cost for 6 by 4 inch image at 150 dpi resolutions? First, You must determine the image size in pixels, then calculate the file size in your memory space. So, let's do this. The image size in pixels will be the printed size image with the DP resolution were 6 x 150 dpi by 4 x 150 dpi. So you get the image size is 900 by 600 pixels. Next, calculate the memory cost. We have learned this in the previous video that the file size is determined by width, height and color bit depth. Since this is RGB color image, so RGB color is 24 bits or equals to 3 bytes. Remember that 1 kilobyte is equals to 1024 bytes. So the total memory cost for this image is 1.5 megabytes. So, please don't confuse with image size and file size. Image size refers to the dimensions of the image, height x length, while the file size is about how much space the image takes up on a hard drive, kilobytes or megabytes. Okay, that's all for Chapter 4. Hope you enjoy this video. Take care everyone.